In my introductory video, I wanted to give you more of an intuitive feel about eigenvectors and eigenvalues. And what that means is after a matrix transformation, any vector that's still pointing in the same direction is an eigenvector. And how it gets stretched or scaled is the eigenvalue. A more formal definition of each of those terms: an eigenvector of an n by n matrix, so they must be square, has to be a non-zero vector, so the zero vector itself can't be an eigenvector, such that this equation is true. Notice this equation is just a modified version of our classic matrix equation. Matrix times a vector equals a final vector, which this is. And so what you're seeing is whatever this first vector is, it's the same one over here being scaled by something. So this is the eigenvalue, where this is the eigenvector. A scalar lambda is called an eigenvalue of a matrix if there's a non-trivial solution to this matrix equation. So we're going to look at a few examples and we'll see what's going on with this equation and how it can help us with some of these problems. So right off the bat, I'm giving you a square matrix. I'm giving you two vectors, and the question, could either of those be an eigenvector? So how can you just check? If you're given all the parts, how do you know something is an eigenvector of a matrix? Well, let's try that first one. These are pretty straightforward. We're just going to solve this thing. We're just going to take matrix A and multiply it by each of those vectors and see what happens. So matrix A times vector U gives us 6 and negative 30, 30, negative 10. And what do we notice about that answer is that it is a scaled version of the input vector. In fact, we could say it is negative 4 times this original vector, which is just negative 4 of the u vector. If that's true, the answer is yes, it was an eigenvector. Let's try the next one. Here comes the v, and here we go. 3 added to negative 12, 15 and negative 4, and clearly by inspection you can see that negative 911 is not a scaled version of the v vector, so the answer is no. One thing I want to point out, so what we know then is there's at least one eigenvector for this matrix. There could be another one, but we know it's not v, and this eigenvector has an associated eigenvalue of negative 4. In my introductory video, one thing I pointed out is sometimes you can just see the eigenvalue in a matrix. Notice negative 4 is clearly not indicated at all here. The only time I said you can see an eigenvalue is if a matrix is an upper or lower triangular form, which this clearly is not. All right, example 2. Same matrix. Now, let's show that 7 is an eigenvalue of this. And here's where that equation really comes in handy. So I now have, there's my A matrix. We're asked to show that 7 is an eigenvalue. So let's plug in what we know. I won't put the matrix in yet. We'll just put a 7 here. And let's rearrange this in a friendly form, bring everybody to the left side. Now remember what this is. This object is a vector. This is a scaled vector, and so the result ends up being the 0 vector. Now, we're going to, let's factor out that x vector, leaving a minus, now remember, that's 7i. the identity matrix. That doesn't make sense. You can't just subtract a number or a scalar from a matrix. It has to be another matrix. And that's where we're going to pick up from here. One thing we learned in the definition of an eigenvalue is that, notice this is a homogeneous equation. We know there's a trivial solution, but what I want to know, is there a non-trivial solution? Is there a vector that's not the zero vector that can still make this true? And if there is, then 7 is an eigenvalue. So here's what we got to figure out. Let's take my A matrix, and we're going to subtract 7 times the identity, which would just be 7 times 1, 0, 0, 1. And let's see what that looks like. 1 minus 7, 6 minus 0, 5 minus 0, and 2 minus 7. Well, at this point, we can answer the question, is 7 an eigenvalue of A? The answer is yes, since the columns are linearly dependent. Just by quick inspection, the second column is just a scaled version of the first. So if that's all we're asking for, is, yeah, it is. Why? Because of this dependence, we know there's going to be a free variable, which is going to give us multiple infinite solutions. So we're done. But let's take it all the way. Let's go ahead and find the eigenvector associated with this. So if we were to take this new matrix, which again is not the original one, but it's what we're going to use then to find an eigenvector. So again, that's tells me we're going to row reduce this. You'll find quickly we get this. Again, if I were to call out my two variables, the second one is free. My first one would be positive one of those. So if we unscale x2 from that solution, we're left with the vector 1, 1. Now, there we go. We can say that 1, 1 is the eigenvector corresponding to the eigenvalue of 7. One side note, though, is there's not just one eigenvector for each eigenvalue. This x2 is a reminder that you could scale this, and then that would also be an eigenvector. So any scaled version of this would be okay. We usually work with what we're given, but there may be a reason why we maybe want to scale it and clean it up a bit. So, so let me just say this, that 1, 1 is an eigenvector. And again, that qualifier is an eigenvector, not the eigenvector, corresponding to the eigenvalue 7. All right, third example. So we're going to bring in some language we're familiar with. We're asked to find a basis for the eigenspace. That sounds like a subspace, and so all the language of subspaces is now coming to hit this world, corresponding to each list an eigenvalue. So, given a matrix and two eigenvalues, how will we find a basis for each one of these? Well, we'll just quickly get there. If I take my first one, you'll remember from example 2, we ended up just subtracting my original matrix minus a scaled version of the identity matrix, and we scale it by an eigenvalue. Well, the first one just being 1 doesn't change it at all. It looks just like this. Let's subtract. And good. Quickly row reduce for you. You get 1, 2/3, 0, 0. Again, let's see if we can quickly get there. That would give me a free variable of x2. leaving a 1 down there, and then the top x1 would be negative 2/3, if you can follow that. And so we could say a basis for this is negative 2/3 1. But this is where I can tell you, you can scale that if you'd like. I prefer not to see fractions, so how about we just scale by 3, and we'll have negative 2, 3 to serve as our basis for the eigenspace corresponding to 1. So I'll just put a note. That's for lambda 1. One more time. We start back with the original matrix. We subtract the scaled version of the identity with 5 this time. So 2, 4, negative 3, negative 1, negative 6. Row reduce, 1, 2, 0, 0. That gives me another free variable at x2, which puts a 1 down in that spot. My top solving for x1 will give me negative 2. And this time I'm okay with that. No fractions to clean up, so we would just leave it. Negative 2, 1 is a basis for the eigenspace associated with lambda equals 5. Last example. Let's check out a 3 by 3. Same question. Let's find a basis for the eigenspace associated with the eigenvalue 3. So, grab the A matrix, subtract the scaled identity, this time 3 by 3. And we quickly get 1, 2, 3 across the top, negative 1, negative 2, negative 3 down the middle, and 2, 4, 6. If we row reduce that, we still get 1, 2, 3 across the top, and you can kind of see it visually. If you just add 1 to 2, you get a row of zeros, and if you multiply by negative 2 and add, you get a row of zeros. So notice this time, of my 3 variables, 2 are free. So let's call those out. And then what is my x1 is negative 2 x2s minus 3 x3s. If we unscale those, we're left with negative 2, 1, 0 scaled by x2. And we've got negative 3, 0, 1 scaled by x3. And so the basis for this eigenspace is actually 2 vectors. So a 2-dimensional basis, it's a plane through the origin, and we're good to go.